Hello, welcome to your week 6 lecture video. I hope you all had a great weekend. We're going to look at 3 chapters this week. 8, the network layer, 9, which is ARP, and 10, which is basic router config. And I might do a packet tracer thing at the end if I remember to. I usually do for the end of chapter 10. Next week, you will have a single chapter and a quiz, so look out for those. So the network layer is, normally at this point I would ask you what layer of the OSI model. I'm going to pause and let you think about that, and I'll give you the answer if you want. Or I guess I'll give you the opportunity to pause. Layer 3, right? So that means we're looking at IP addressing. Layer 3 addressing, IP addressing, logical addressing, all the same thing. So we're going to look at how the network layer uses IP to provide reliable communication. We'll look at IPv4 and IPv6. We're going to look at routes and routing tables and how routers work. Lots of really important stuff. This is the foundation for what you're going to be learning next semester, so it's very important. So the network layer provides services that gives you end-to-end communication between devices over the network. You're going to see 2 protocols here. IPv4, well actually you're going to see a few more than 2, but 2 IP protocols here. IP version 4 and IP version 6. They're the 2 that we use. These give you your addressing for your end devices. Also at the network layer we get encapsulation, de-encapsulation, and routing. Anything to do with routing is a layer 3 protocol. So when we come down from the transport layer, right? IP encapsulates that segment into a packet. Now this could be in either IPv4 or IPv6 packet. Doesn't have any effect on the layer 4 segments, and this gets passed down to layer 2, which we looked at extensively last week. At layer 2 we're dealing with frames, right? Now if you recall with that frame at layer 2, that gets analyzed at each hop, stripped off, and a new one gets encapsulated, right? Not so with IP. The IP packet is examined by every single layer 3 device that traverses through the network, and the source and destination addressing, unlike frames, does not change at all. Unless you're using NAT, and we'll look at that maybe later. Not in this module. So IP has low overhead. It can be described as connectionless, a best effort protocol, and media independent. What the hell does that mean? Here we go. It's connectionless, right? IP doesn't establish the connection before sending the packet to the destination. It relies on other protocols to do that, transport layer protocols. There's no control information with IP for synchronization and acknowledgements and stuff like that. Again, other protocols are coupled with IP to take care of that. The destination receives that packet when it arrives, but there's no notification that it's even coming. It just sends the data. If we need connection-oriented traffic, then we deal with another protocol at the transport layer, usually TCP, and that coupled with IP. That's why you tend to see TCP IP as a protocol suite, right? TCP will take care of the connection-oriented portion. IP operates independently of it. And if you don't need that, then you're using UDP, right? We're going to look at the transport layer, I think, a bit later. Next week? Maybe today? I don't remember. It's coming. It's coming somewhere in the slides. We're just not there yet. Not in this set of slides. So IP is a best effort protocol. It doesn't guarantee the packet's going to be delivered. It has no mechanism to verify that data has been sent and received and resend data that's not been sent. There are no expected acknowledgement packets. And when it sends a packet, it doesn't even know if the device on the other end is online, if it's operational, if it even receives the packet. IP doesn't know, and IP doesn't care. In fact, some packets might be lost on their way to the destination. And that's where you layer it with TCP, right? It's unreliable because it can't track any of that stuff, right? Because there's no way for acknowledging whether packets were received. It can't manage or fix undelivered or corrupt packets because it has no mechanism to do so. It can't retransmit any data. It can't even realign them if they're alive out of sequence. Other protocols have to do that. TCP, right? I've mentioned that a few times now. And it's media independent. It doesn't matter what type of network you're using. IP works the same on copper, fiber, wireless, coax, copper Ethernet, serial, well, fiber's optics, right? Anything. IP works the same on any media. It doesn't matter what the type of frame is. That's the data link layer's responsibility. And it doesn't matter what data it's encapsulating from the upper layers. IP doesn't care. Its job is to just assign the packets and pass them on. That's why it's so popular. It does its job very, very well. Now the network layer will establish the MTU, the maximum transmission unit. And it receives that information from stuff sent, control information sent up from the data link layer, and then establishes that size. IPv4 might fragment packets. It might split packets into smaller packets to accommodate the maximum transmission size if it's smaller. This will cause latency. IPv6 doesn't do this, just IPv4. It's an important thing. Why would this happen? Because you've got two connections on either side of a router, and one's slower than the other, right? The router goes from a slow connection to a fast connection, or a faster connection to a slow connection. Things have to be fragmented. So now that we've talked about IP a bit, we know IPv4 and IPv6, right? Let's look at packet headers and what they look like. We looked at frames last week. We're going to look at packets. IPv4 is the primary communication protocol for the network layer. Despite the fact that we're out of IPv4 addresses, it's still very commonly used in industry. And the header for IP has many purposes. It ensures that the packet's sent to the correct destination and in the correct direction. It contains all the information for the various fields at the network layer, and it's used by every single layer 3 device that handles that packet. Layer 3 device being a router, typically, although it could also be a layer 3 switch. Also, PCs and servers, right? They operate at layer 3. Anything that has IP addresses is a layer 3 device. IPv4 headers are in binary, right? They're represented in binary. It doesn't look like in this pretty format that we see on the screen. This is our representation of it, so we can visually understand how it looks, right? But it's binary. It's just ones and zeros. It has a whole bunch of information. And the diagram's read left to right, 4 bytes per line. But the two most important ones, I'm going to say 3, right? The Cisco slides say 2. I think there's 3 here, really. Source and destination IP address. Also version, because that'll tell you if it's version 4 or version 6. Now, the protocols may have, this protocol field here, may have one or more functions, depending on how things are, well, depending on what's being sent. So that version, it's going to be 4 or 6. This is IPv4 though, right? IPv6 headers look a little bit different. So this is going to be 4 in this case. Differentiated services, that's used for quality of service, right? If you're going to use quality of service rules to prioritize certain type of traffic, then you're going to have stuff here. The checksum is used for error detection in the header itself. The time to live is the layer 3 hop count. When that hits 0, the router discards the packet. The protocol indicates the next level protocol, the layer 4 protocol, transport layer, whether it's TCP, UDP, ICMP. And then your source and destination IP addresses, those are 32-bit addresses. Now, IPv6 was designed as the replacement for IPv4, right? And when they created and developed IPv6, there were a number of efficiencies that were built into the protocol to make it function a bit better, as we're going to see. Why did we migrate? We ran out of IPv4 addresses. Does that mean you can't get any? You can totally get IPv4 addresses, right? We're going to look at IPv4 and IPv6 a little later and more in depth, but you can't go to an authority and acquire a public IPv4 address because they don't have any to send you. What you can do is go to somebody who's selling off their IPv4 address in space and say, hey, I want an IP address, and they go, yeah, here you go, give me some money, right? That's how it works. But as we're going to see and talk about later in the semester, we've pretty much run out of IPv4 addresses, right? IPv4 lacks end-to-end connectivity. You've got public and private addressing and NAT. That's how your home network works, right? You've got public or private IP addresses internally, and they're NATed at your router to a public address, so they get out on the internet, because those private IP addresses aren't routable on the internet. Now, NAT was intended as a temporary solution because we ran out of IPv6 or IPv4 addresses, but it creates more issues. Causes latency. It makes it difficult to troubleshoot some things. There's benefits too, but there's side effects. Now, when IPv6 was developed by the IETF, it was developed with the limitations of IPv4 in mind. Some of those being, we've got a lot more space. IPv4 addresses are a 32-bit address space. That gives us 1 billion IP addresses, just IPv4. IPv6, however, has 340 undecillion addresses. And if you look at the bottom there, like look at 1 billion, that's 3 or 9 zeros. Look at undecillion, that's 3, 6, or sorry, 9, 18, 21, 27, 28, 29, 30, 31, 32, 33 zeros. 1 and 33 zeros. 36 zeros. I think I miscounted. It's way bigger, right? It's way, way bigger. So we have a lot more addresses. It has improved packet handling because we've got fewer fields. There's less necessary information in a packet. It's less overhead. They're quicker to process. And NAT is completely eliminated. Somewhat anyway. You can still use it, but it's not required. You don't actually need it, because you can just have a public IP address. Everybody can have one. It's unnecessary to have internal private addresses. So here's what they look like, right? An IPv6 header, and again, it's binary. This is what it looks like for us. It's simplified. It's not smaller. It's still 40 bytes. It says or octets. Yeah, okay. That's going to be 5 octets, right? 5 times 8 is 40? Yeah, 5 octets. A bunch of the fields were removed to improve performance, like the flag, the fragment offset, the header checksum. We're not bothering running a checksum on the header anymore, because TCP is going to take care of that. If it's a bad frame, it'll just drop it, right? We don't need to deal with that. The significant fields we have, that should say IPv6 address, right? The version, so it's going to be 6 instead of 4. Traffic class is still there. It's used for quality of service. The flow label informs the device how to handle identical flow labels the same way. Payload length, so it's a 16-bit field and it indicates the length of the payload, the data within the packet. Next header, that identifies the next level protocol. Hop limit replaces the hop count time to live field. Does basically the same thing though. And then your source and destination, that's a typo on the slide, it should be IPv6 address. Those are 128-bit addresses, not 32-bit, right? Now that packet might also contain extension headers that give you additional network layer information that's totally optional. And these are completely optional. They don't have to be there, but they could be. These are placed in between the IPv6 header and the payload. And these can be used for security, fragmentation, supporting mobility. There's a variety of different uses for these. Unlike IPv4, routers don't fragment IPv6 packets. They stay the same size. They're not broken down. I would normally pause to ask you if that makes sense, and hopefully it does. I'm going to pause for some water, and then I'll continue. So we're looking at how hosts route packets. Packets are always created at the source, at whatever device is initiating the traffic and sending it. Each host device creates its own routing table, and a host can send packets to one of 3 types of destinations. Itself, using the loopback IP, that's 127.0.0.1 for IPv4, or :1 for IPv6. To local hosts on the same LAN, the same network segment, or remote hosts, literally anywhere else. That's not itself and it's not on the same LAN. It's a remote host. The source device determines whether that destination is local or remote. How does it determine it, you might ask? Well, in IPv4, it looks at its IP address and subnet mask and compares it to the destination IP address. The subnet mask with IPv4 tells the device what portion of the address represents the network and which portion represents the host. So it can look at the mask and compare those IP addresses and determine if they're on the same network or not. IPv6 does things a little bit differently. It uses the network address and the prefix, which does basically what the subnet mask does, and it can figure that out. Now local traffic, that just gets sent out the host interface and it's handled by an intermediary device. Remote traffic, that gets forwarded directly to your default gateway, where it goes outside to the internet. Yay. Now, a router or a layer 3 switch can be configured as the default gateway. To be a default gateway, it has to have a couple things. Your IP address has to be on the same subnet as the rest of the devices in the LAN. Otherwise, traffic's not going to get there, or it's not going to get anywhere. It can accept data from the LAN and forward it off the LAN, right, to the internet, to external networks. It can also route to other internal networks. If a device doesn't have a default gateway or it's misconfigured, then it's restricted to just communication on the local LAN, the local network segment. It can't communicate beyond its subnet. With IPv4, hosts either know about their IP or their default gateway because it's been statically configured or it's been provided by the DHCP server. If neither of those is true, and it doesn't have one, it can't communicate outside of the local network. In IPv6, this can be determined, determined is the right word here, through a router solicitation package, or you can also configure it manually. We don't use DHCP for that, with IPv6. Now this default gateway shows up as a static route It's the last resort route in the routing table, and in Cisco IOS we refer to this as the gateway of last resort. All devices on the LAN need a default gateway if they want to communicate outside of the local network segment. When you're looking at routing tables in Windows, you could use netstat-r. We see our routing table here, and we've got our destinations, we've got our subnet mask, our gateway, and the interface to send that traffic out. And you're going to notice this this destination of all zeros, this quad zero network, and this same quad zero mask, that's going to be the default gateway. And it shows up the same in Cisco, Linux, Windows. It's always going to be that quad zero in your routing table. That's your default gateway. Hopefully that makes sense. So how are packets routed? What happens? Well, we've got a router. We've got a PC that's trying to send a packet, right? It's in that that packet, that layer 3 packet. We have a source and destination IP address. The source IP address in this case is going to be 192.168.10.10, right? Because that's the PC that's sending the data. The destination IP is 10.1.1.10. It looks in its routing table and determines I need to send that to the default gateway, so it forwards it there because it has one configured. The default gateway looks at that information, looks at the destination IP address, realizes it's not an address, and then it begins looking through its routing table, or not an address, not a local address. So it looks through its routing table to determine if it knows about that network and how to get there. And if we look at the routing table here, we see it's going to be the network portion. It's going to be a /24. It's going to match this entry here, right? 10.1.1.0/24. And the next hop interface is this one here to router 2, this IP. So it's going to forward the packet onto router 2. Router 2 is going to know what to do with it, right? Now, routers can learn about networks in one of 3 different ways. Different types, different ways they can be added to the table, right? We're not looking at routing protocols, we're looking at the types of routes that you see. They could be directly connected. These are automatically added when you configure an interface with an IP address and bring it administratively up, and it's got a cable plugged in, so it's in a up status, which we're going to look at a bit later. They could be remote connections. So these are routers that the routes that the router does not have direct connections to. These could be learned in one of 2 ways, either manually by issuing a static route, which you're going to learn how to do later, or dynamically using a dynamic routing protocol, which you're going to work with next semester. And finally, there's a default route that could be considered. This is your gateway of last resort. It's kind of like your default gateway in a PC. It's where to send traffic if there isn't a match in the routing table. And you might have one of these configured on your border router that's going out to the internet to say, hey, if it doesn't go anywhere in my organization, it must be going to the internet, so send it there. And then you can then propagate that route internally using routing protocols. Static routing must be done manually. And it has to be changed by the admin when there's a change in the topology. This isn't used commonly for anything other than configuring a default static route, like that example I just gave you, right? That this is our path to the internet, so we're going to set a default static route here, and then we can propagate that internally using dynamic routing protocols. Static routing is okay for small networks with 0 redundancy, but as soon as you have redundancy, or as soon as you have anything else, you generally want dynamic routing, which you're going to learn more about next semester. We're going to talk about it today, but you're not going to do anything with it this semester. You're not going to do anything with static routing either this semester, honestly. Dynamic routing, however, what you do with any dynamic routing protocol you configure is you tell a router to share the routes that it's directly connected to with neighboring routers that are appropriately configured to do so. And this allows routers to update their routing tables on their own, share information with each other, and use this to discover remote networks. Allows them to determine best paths through the network, and find new paths when the topology changes because an interface goes down or a cable breaks or something. Dynamic routing can also share static default routes with other routers, which is why it's useful to learn static routing before you jump into dynamic routing. Hopefully that makes sense. When you look at a routing table in Cisco IOS, you do it with the show IP route command. And you're always going to have this bit with the codes at the top, so you don't need to remember what the different letters mean. It's always going to be there, but you're going to get to know these as you see them. L indicates that it's a local interface, a directly connected interface. Remember I mentioned that when you configure an interface and you bring it in an up status, you're actually going to get one of these, and you're going to get a directly connected network indicated by a C as well. So two of these, an L and a C, for every single interface that you have on the router. Then you might have static routes that were manually configured by the admin. They're going to show up with an S. Those learned through OSPF, which stands for Open Shortest Path First. It's a dynamic routing protocol. It's a very popular one. Those show up as an O. So we see we have one learned through OSPF here and one static route, and I'll talk about the asterisk in a second. And D will indicate EIGRP. And you notice there's a whole bunch of other ones up there that we haven't talked about. OSPF and EIGRP tend to be two of the more popular routing protocols that you're going to configure in semester, well, I would say semester 3, I think it's semester 4, your third Cisco course. Anything with a star or an asterisk next to it indicates that that's the default route. That's where we're going to send data if we don't have a matching route. It just goes there. And if you don't have one of these, then stuff just gets dropped if it doesn't match anything. So you tend to want one of these. And that is the end of the first of 3 chapters. I'm going to pause and get set up for our next set of slides. All right, so we just finished chapter 8. We're going to look at chapter 9 now. In chapter 8, we talked about network layer and addressing that you find at the network layer, layer 3, right? IP addressing. Now we're looking at ARP and neighbor discovery, which is the IPv6 thing we use, and D. So we've talked about MAC addressing, we've talked about IP addressing. MAC addressing you find at layer 2, the data link layer. It's our physical addressing, right? Layer 2 addressing, physical addressing, MAC addressing. You see those 3 terms used interchangeably. IP addressing, layer 3 addressing, or logical addressing. You tend to see those three terms used interchangeably as well, right? ARP and neighbor discovery are what tie the two together. If you're using IPv4 or IPv6. So, we use these 2 types of addresses, right? Layer 2 addresses, those are your MAC addresses or physical addresses. Layer 3 addresses, these are your IP addresses, your logical addresses, right? The layer 2 addressing, those are the things we see in our frames that we've talked about. Layer 3 addressing we see in our packets, as our source and destination IP addresses in a packet, and source and destination MAC addresses in a frame, respectively. When the destination's on a remote network, the destination MAC address is always going to be that of your default gateway. ARP, if you're using IPv4, is used to associate IP addresses to MAC addresses within the local network. If you're using IPv6, we use ICMP v6 instead, or neighbor discovery. and that associates IPv6 addresses with MAC addresses, so devices can build their tables, ARP tables, as we're going to look at in a minute, like right now. So ARP is Address Resolution Protocol, and this is what a device uses to determine the destination MAC address of a local device when it knows the IPv4 address. It gives you two basic functions. It resolves those IPv4 addresses to MAC addresses, and each device maintains its own ARP table of mappings from IPv4 addresses to MAC addresses, so frames and packets can be forwarded quickly. To send a frame, a device searches its own ARP table for the destination address, and when it finds one, it pulls its corresponding MAC address, builds the frame, and sends it on its merry way. If the packet's destination is on the same network, the device will search its ARP table for the destination IPv4 address. If it's on a remote network, though, it looks in the ARP table for the IPv4 address of the default gateway. And if it locates that IPv4 address, whatever MAC address that corresponds to it in the table, that's going to be the destination MAC address of the frame. If there's nothing in the ARP table that matches, the device will send out an ARP request, which we're going to look at in a little bit. Now, of course, these frames can't be permanent, right? Because it would just consume a ton of resources. So entries from the table are removed when the ARP cache timer expires. This cache timer differs depending on the operating system. You can also flush these manually or clear them. We refer to that as flushing the ARP table usually. If you want to look at your ARP table, there's a couple commands you can do that with. In Cisco, we can use show IP ARP. You're going to do this in the lab. And we see our IP to MAC addressing binding in our ARP table. In Windows, you issue the command in a command prompt, ARP-A, and again we see our IP address to physical address, right? Our MAC address, layer 3, layer 2, whatever way you want to look at, right? It's the same binding. Now, I mentioned an ARP request if a match isn't found. Well, how do those work? ARP requests are broadcast traffic. They're received and processed by every device on the local network. As you can imagine, if you have too many of these, it can reduce the performance of your network. ARP replies can be spoofed by somebody trying to hack your network. They can inject some false information in there, and that's known as an ARP poisoning attack. Enterprise level switches have mitigation techniques to protect against these. We're going to look at them later. I don't believe later today, but later in the semester when we look at security. Now, notice when we're talking about ARP, I was just talking about IPv4. It's because for IPv6, we don't use ARP. We use neighbor discovery instead. It's a little bit better. Neighbor discovery for IPv6 provides everything that ARP does, address resolution as well as router discovery and redirection services. Their ICMP version 6 packets. We use neighbor solicitation packets and neighbor advertisement packages for device-to-device messaging, such as address resolution, and router solicitation and router advertisement packets or messages. These are used for messaging between devices and routers for router discovery, and ICMP v6 redirect messages. These are used by routers for better next hop selection. So IPv6 uses neighbor discovery to resolve MAC addresses of known IPv6 addresses, just like we use ARP in IPv4, and it builds a neighbor discovery table, not an ARP table. Neighbor solicitation messages are sent using multicast IPv6 addresses. These are or multicast, right? They're not broadcast, they're multicast, so they're a little bit better. And that is the end of our second chapter this week. So again, I'm going to pause, get set up for our third, and we will continue. We're just flying through this. It's great. All right. So module 10, chapter 10, whatever you want to call it, basic router configuration. So we talked about a bunch of things so far, right? We talked about ARP. We talked about network layer and IP a bit, and routing. Now we're going to talk about how to configure a router, which we've configured switches. Routers are pretty much, the basic configuration is pretty much the same. There's just a couple different things we have to do, like configuring interfaces in the default gateway and interfaces with IP addresses, which again you kind of did in switches with virtual interfaces, but on routers you're going to have lots of interfaces you want to configure. So the initial router settings are basically identical to what you're going to do on a switch, just slightly different values, right? Your prompt is router instead of switch by default, because it's a router. So you're going to do things like configure the device name with the host name command, set the enable password, set your line and console, or your console and VTY passwords. You might want to set SSH or configure SSH over Telnet, because SSH is secure and Telnet isn't. And enable a password encryption service on the device so all your passwords are encrypted and not in plain text. And provide a banner message of the day, which provides legal notification to anybody who hacks it, right? Or tries to hack it. That's the standard stuff that we seem to do. Just like a switch so far. Nothing different yet. So here it is. Of course, we save it at the end, and we're good to go. Now, here's where things are going to get a little bit different. We're going to configure interfaces with IP addresses because it's a router. It's a layer 3 device. That means we have IP addresses that we can associate with the router. And we have to, or it's not going to work. So first you go into interface configuration mode. Interface from global config, right? Interface followed by the type and number. You want to give it a description. It's a good practice because it makes your configuration a little easier to read. The description usually just tells you what that connection is linking to. Then you can assign it an IPv4 address with the IP address command, and you provide it the IPv4 address in the subnet mask. IPv6 address will do the same thing for IPv6, and you provide it the IPv6 address slash and the prefix length. And then you have to bring the interface administratively up with the no shutdown command. Now, why no shutdown? That seems weird. Well, no is a keyword, a key command that will invert any command in Cisco IOS. To shut down an interface, you just type shutdown. Instead of giving you a different command to bring it up, they just said, no shutdown, right? It's the opposite of shutdown, bring it up. That makes sense. That's why. So we're going to configure in this example here. We've got gigabit 000 on router 1. That's this one here. We're going to configure it. So interface gigabit Ethernet 000 or G0/0/0 would be the shortcut. Give it a description. So this is the LAN link, right? Give it its IPv4 address. So IP address. The IP address 192.168.10.1 with the subnet mask. It's a /24, so it's going to be 255.255.255.0. And its IPv6 address, because we're configuring a dual stack configuration here, which means every device is going to have an IPv4 and an IPv6 address, which is a common thing. IPv6 address, and see we have the address, a slash, and our prefix, and then bring the interface up. No shutdown. And type exit, or you can type end, right? We'll take it right back to the beginning. And we should see that the interface changes from down to up, and the line protocol is up. And then we're gonna confirm it, which we should look at shortly. We're going to configure gigabit 001 same way, right? You could do this from global config. You could actually just do this from this prompt here. Skip the exit, type interface gigabit 001, and go right into that interface configuration mode. Then do all the same things. Give it a description, give it an IPv4 address, give it an IPv6 address, and bring it up. And then usually if I'm done, that's it. Two interfaces on the router, that's all we're configuring. I always want to confirm it. And I tend to use show IP interface brief, and that will show us, yes, here's our interface, here's its IP address. It's administratively up, which means we've issued the no shutdown command, and the line protocol is up, which indicates that there's a cable plugged in and the devices on both ends of that cable are on. If you brought it up and you see the line protocol is down and you're expecting it to be up, double check the cabling, make sure your cables are plugged in the right place. Maybe swap out the cable, maybe you got a bad cable, and make sure that you configure the device at the other end of the connection, because maybe you didn't. To verify IPv6, it's a different command, show IPv6 interface brief. And we see all the outputs there, but it's formatted a little bit differently because it's IPv6. So we see this administrative and line protocol. It's just simplified to either up, or down, or some variation of that, right? Some combination of up or down in those two spots. We see its link local address, and we see its global unicast address per interface, right? Each interface is going to have one. That's how IPv6 works. So show IP interface brief and show IPv6 interface brief. Those are usually my go-to. You might want to look at the routing table as well. Show IP route or show IPv6 route. If you're dealing with IPv6, IP of course for IPv4. Show interfaces will give you all the information about all the interfaces on the device. IPv4 only. Show IP interfaces gives you the IPv4 information for the interfaces on the router, and show IPv6 interfaces, same thing but for IPv6. So here's an example. We just looked at an example of this, right? Show IP interface brief and show IPv6 interface brief, which I just kind of went through. Here's what looking at the routing table looks like. So we see we've got our connected route and our local IP address. So our interfaces are up and our routing table is working. There's no gateway of last resort set, so we haven't set a default gateway or a default static route. And there's no routing protocol configured here, right? And here's the IPv6 routing table. And if you look at show interfaces, you're going to see a whole bunch of information per interface in a long kind of way that you can kind of read in and see what's going on, right? But the important stuff here, we've got our interface. It's administratively up. The line protocol is up, which I've already mentioned what that is like 3 or 4 times. We've got our hardware, so it's an ISR 4321 router, right? There's its MAC address. It's got a description. It's got an IP address. And a whole bunch of other stuff, right? You can see all kinds of stuff. We've got ARP information. We've got its speed and duplex. Lots of stuff, right? For any more in-depth troubleshooting, this is kind of what you want. Here's the IPv4 information for your interfaces on the router. So we see, again, similar stuff. Our interface, it's administratively up. The line protocol's up. There's its IP address and subnet mask in CIDR notation. There's the broadcast. Helper address, that's something you're going to learn in a later semester. That's for setting a DHCP relay agent for if you've got a DHCP server that's on another subnet, you need to configure an IP helper address. And you can see a bunch of other stuff here too, right? Show IPv6 interface brief. Similar information, just IPv6. And we see the different groups that the interface is a part of. Wow, we're flying through this. Now, default gateways. Default gateways are useful things that we've talked about a few times already in the last 45 minutes, so you should know what this is. They're used for hosts to send packets to devices that are on another network. Without a default gateway, you can only communicate on your local subnet, right? You can't do or can't connect outside the local subnet. Now you might want to configure these on a switch, and in fact you already have in the labs as part of the configuration. Why would you want to configure these on a switch? Well, if you want to remote access that switch to manage it from another subnet, then you have to provide the default gateway to the switch, and that's going to be the IP address of the directly connected router. You do that in global configuration by issuing the command IP default gateway, and then give it an IP address of that interface that's the default gateway, and you'll be able to remote access into that switch and do things. Sound good? Hopefully. Right then. That brings us into the end of chapter 3. I'm going to set us up for a quick packet tracer demo, and then you're done for the week. So yeah, give me a minute. All right, I'm all set up and good to go. So what I'm going to show you here, we're just going to do a basic router configuration with a PC. I'm not going to stick a switch in the mix. And we're just going to do this straight up here, right? Now, I'm going to do some subnetting, which I'm not going to get into the details of at the moment. 6 8 dot 0 dot 0 slash 25 and 192. Oops. Let's see if I can type. So this subnet I'm going to put here. Subnetting is going to make more sense in a few weeks. This subnet I'm going to put up here in the form of a loopback IP. I'm going to use the last usable IP addresses on my router, first usable IP on our PC, so that means that this interface is going to be the default gateway. And honestly, if you can do the configuration that I'm about to do right now for your practical test, you can easily get an A, because it's going to be the same config. PC connected to a router with a loopback. So, let's have at it. I'm going to try to do this in my head without writing it down. We're going to say no to that, right? And there we go. We've got our initial prompt. Type enter to get started. Enable, configure terminal. I'm going to give it a host name. I'm going to skip the standard password and stuff just to speed things along. First thing I'm going to do, interface gigabit 000. I'm going to give it an IP address of 192.168.0.126, with a subnet mask of 255.255.255.128, and bring it up. We see our line protocol changed up. Our lights are green, it's up. I'm going to enable a loopback interface, and I'm going to give it the last usable IP address in the other subnet. So that's going to be 192.168.0.254. Same mask, no shut. And show IP interface brief. And we see its status is up. If I make this a little bit bigger, there we go. Status is up, line protocol's up. Yeah, we're good to go. I could do show IP interface gigabit 000. And there's all the information on 000. interface loopback 0, which didn't work for some reason. Yeah, we didn't get anything there. That's weird. Weird. Let's look at our routing table too. Show IP route. We see our IPv4 routing table. We're good to go essentially. Now, that was like 2 minutes, not even. Jeez. We go into our PC. We're going to give it the first usable IP. We're going to give it the subnet mask. Right, we're going to change that to 128. And the default gateway, that's going to be this IP here. Without that, it's not going to be able to connect. Then we go to our command prompt. I'm going to type IP config. See, there's my IP. We should be able to ping 92.168.0.254. It's working. That means we can ping the loopback. We should be able to ping our default gateway, which is what you would try if you couldn't ping that loopback. There we go. We're good. A warning when you do this, that first one might fail because ARP. Right, that's why it fails. And we learned all about ARP in this week's lecture, so you should know what I'm talking about, right? The amount of time for that ARP request took too long and the first packet failed out. The first ping reply, or echo reply, because that's what ping is. Echo request, echo reply, right? Two messages that are sent. Honestly, if you can do what I just did in like 2 minutes, you're gonna have longer than 2 minutes, right? But if you can do what I just did, configure this router with a physical interface and a loopback, configure this PC, ping the loopback with the basic configuration as well, your standard passwords and stuff. Lock down your line protocol and your console port and things like that. That's your practical test in a nutshell. If you can do that, you can get an A on the practical with some subnetting that we're going to look at later in the semester. It's not that bad. We're going to go over lots of practice between now and then. So with all that in mind, take care. Be safe. I hope you had a safe and happy weekend. And I will see you in this week's lab. Bye for now.